So today is the 22nd. And let me copy the function before I forget. It was 2x minus 4 over x plus 1. Yes, I'm ready. Greg, go ahead. You had something?
Yeah, you had to find the absolute max and min for the natural log of x squared plus 7x plus 14. And on the interval, close negative 4 to 1.
Excellent. Okay, so we are given a function, we are given a closed interval, and we're going to ask find the absolute max min. I promised a quiz today, but my colleague from the copy center did not get the message because he was on vacation or something happened yesterday and today. So please get ready for some little quizzes from this chapter on Thursday. Okay, so we are given a closed interval. We don't discuss that. We have, that's all we have. In other words, negative 4 to 1. This is it. And in order to find max min, the first thing I need to determine is, I would have said, let's find the domain, but there is no need. We are specifically told x is between negative 4 and 1.
What's the last number of that?
14. So all we have to do is find the derivative, which is 1 over x squared plus 7x plus 14 times, can anyone help? Anyone? Which is? Very good. And we have, remember, f prime of x has critical numbers coming from two sources. Potentially, it doesn't have to have any critical number. But if it does, it may have critical numbers coming from the equation f prime of x equals 0 or coming from f prime being undefined. So the first derivative, one more time, I'm going to copy it here, is 2x plus 7 divided by x plus 2 and x plus 5, right? 2 and, no, it's not factorable. Sorry. Okay. I don't know why. I was daydreaming. I thought it was, but no, it's not factorable indeed. So I would have liked it to be, but it's not. Good. So f prime of x, I'll let it dry and I'll come back and write the denominator. So f prime of x is 0 means 2x plus 7 equals 0 or x equals negative 7/2. A fraction is 0 only when the numerator is 0, so I set the numerator equal to 0 and I got negative 7/2. If negative 7/2, which is negative 3.5, is in the domain, then I have to write it. Now, this function that I try to factor in the denominator, but it's not factorable, it's x squared plus 7x plus 14, that is only positive. Because if you're trying to find the solutions for the denominator, with the quadratic formula, let me do that, you will see it has imaginary solutions. As since the leading coefficient is positive, it will always be positive. So x squared plus 7x plus 14, if I want to set it equal to 0, to see if f prime of x is undefined anywhere where the function is defined, then I use the quadratic formula, negative 7 plus or minus the square root of 49 minus 4ac over 2a. So you see that the quantity under the square root is negative, right? 49 minus 56 is an so the square root will be an imaginary number. So this is never undefined. You don't have to cross it out. I'm just saying, in other words, it's not, f prime is not undefined. So there is only one critical number, which is negative 7/2, right here. I have to determine immediately these three numbers, the y values. The y value at negative 4, the y value at negative 7/2 and the y value at 1. Is this clear? Okay, and after that we have to study the sign. Well, but this is always positive. I refuse to study the sign of this. The sign of the entire f prime will be given by this quantity. And since it's a linear function with a positive slope, it must come from and go to right. So I can immediately write this. But I have to find these numbers. And of course, this will be this situation, but I have to make sure that the numbers match, because otherwise I have to go back and start from scratch. So in y equals, and we have natural log, and in parentheses, not two sets, x squared plus 7x and plus 14. And then second in table, and what I need is negative 4, negative 7/2, and the last one is 1. And the values are 0.69, 0.56, and 3.1. So from 0.69, indeed down to 0.56, and indeed up to 3.1. So this is definitely a local min and absolute min. So the answer for this is local min and absolute min, negative 7/2, comma 0.56. Now if they want an exact number, you have to be very careful to read the requirement, right? Because if it says, then you can only plug it in and simplify as much as you can without approximating. So I don't know what they want.
Okay.
Okay, so this is the local min and absolute min, and the absolute max. And they don't want this. I'm writing it because it's important, but they don't. They only want the absolute max and the absolute min. So this will be 1, 3.1 from here. This is the local min and absolute min, because if from 0.69 it drops to 0.56 and then goes up to 3.1. At the end point of the interval, we can have an absolute max, but not local. This is really nothing, because it's really in between these two values. So this is the local and absolute min, and this is the absolute max, 1, 3.1. Is this okay? Very good question. Other questions? Is there anything else you'd like to work on? Anything else you tried? Anything else? Okay, so let's continue then with this function, because we did not finish it last time. And some of you are not here, so I'd rather start from scratch. Okay, so for this function, we're asked to determine everything. First, I'll have to have the domain. Then I'll study the first derivative. Then I'll study the second derivative. And I'll get everything I need, and I'll graph the function. So this is our first major application in this chapter. Okay, ready? What can you tell me about this function when it comes to its domain? That's our first question. The domain is anything but? Very good. Negative infinity, -1, 0, infinity. And since the function is undefined at -1, of course, the derivatives will be undefined as well. Okay, what can we find about the function? From the function itself. Well, we can find the limits here, 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 and here. And of course, x equals -1 will be a vertical asymptote. unless the factor goes away, but it does not go away with anything. I'll give you an example when it does go away. And you'll see what happens then. Okay, so we have to find the x and y intercepts. So these four limits, and plus the x and y intercepts. So can anyone give us the x-intercept of this function? What is it? Very good. When the numerator is 0. So f of x is 0 when x is 2. It comes from here. Only when the numerator is 0, a fraction is 0. And now let's plug in 0. Here's what I do when I plug in 0. So please plug in 0. What do you get? -4. Let's determine the corresponding limits to when x approaches -infinity, when x approaches infinity, when x approaches -1 from the left and -1 from the right. Ready? So limit as x approaches -infinity from 2x minus 4 over x plus 1. Limit as x approaches infinity from 2x minus 4 over x plus 1. As well as limit as x approaches -1 from the left of 2x minus 4 over x plus 1. And limit as x approaches -1 from the right from 2x minus 4 over x plus 1. Remember, first we plug it in. We cannot forget chapter 2. First we plug it in to see what type of limit this is. Because if it's 5, then you don't have to do anything, right? Okay, so in the first two limits, when you plug in, what do you get? Right, because this is infinity over infinity. You will use L'Hopital's rule. When you differentiate the top, you get 2. When you differentiate the bottom, you get 2. So therefore, y equals 2 is the horizontal asymptote. 2, 2, y equals 2 is the horizontal asymptote. Is this clear? Is this okay? Anyone, please? Is this okay? Kyle, is this okay? Anyone? Okay, so now let's determine the limit for the other two. Of course, we know it has to be infinity. I don't know which one. For both, I have to get infinity, but I don't know the sign. So when I plug in -1, the top has to be negative. In both cases, I don't care what it is, but it's definitely negative. But the denominator is 0. So that's why I know, in addition to the fact that it's a vertical asymptote, that's why I know it has to be an infinity. So now -1 from the left means -1 minus -1.1. What is the sign of this with -1.1 from the left? Negative, right? -1.1 plus 1 would be negative. Now with -0.9, -0.9 plus 1 would be positive. So this one has a negative. If you want -0, I don't like to say that. And this one has positive. So the negative of a negative will be, and negative of a positive will be this. So on the left, infinity. On the right, -infinity. There is nothing else we can find about the function from the function itself. I'm done. We're done. For the limits, vertical asymptotes, horizontal asymptotes, x and y intercepts. That's it. There's nothing else. So now we can continue with the first derivative and study it and find critical numbers. So when we differentiate, let me copy the function. I prefer this because, as you know, I don't care for that constant in front. I didn't mean to write 2 again. I meant to write x. So I don't care for that constant in front. It's just a factor. It can wait. Good. So then, when we differentiate, 2 will stay outside. And now we differentiate the ratio. The top prime is 1 times the denominator minus the top times the denominator prime, which happens to be 1, over x plus 1 squared. I cannot stress enough, please do not get tempted to simplify these two. You cannot. This is a term. These are two terms, and those are factors. So we have to go combine like terms, etc., etc. So we have 2, then x plus 1 minus x plus 2 divided by x plus 1 squared. These two luckily go away. The 3 times 2 is a 6. And looking at this, can this be 0? A fraction is 0 only when the top is 0. Can this be 0? No, because the numerator is 6. So it cannot be 0. Now, since it cannot be 0, it doesn't have, the function doesn't have a critical number. If it doesn't have a critical number, the function cannot have max min. But I still have to study the sign of the derivative. So, can anyone tell us what is the sign of this, no matter what? Yes, which immediately says that the function is always, careful, the function is always, exactly. If the derivative is always positive, the function is always increasing. And now, the moment of truth. If these two don't work well together, I have to go back to the drawing board and say I made an error somewhere, something is wrong, start from scratch. So, let's see. From 2 to infinity, what does the function do? Is that supported by the sign? From negative infinity to negative 4 to 0 and to 2. What does the function do? Yes, all the time. So everything is, it works well. Now I'm ready to determine the second derivative. Is this function symmetric? If it has a vertical asymptote at negative 2, it cannot be symmetric. We have to add this in. Not symmetric at some point in time. So I just wanted to finish it up. Okay, so now we are differentiating to find the second derivative. But remember, the first derivative should be written like this. That's the easiest thing to do. I'm not trying to avoid using the quotient rule, but why would I use the quotient rule when the numerator is just a constant? There is no need. So I changed the first derivative into 6 times x plus 1 to negative 2. And now this is much easier to differentiate. So this is negative 12 times x plus 1 to negative 3 times what?
1.
Yes, but we don't have to write it. Excellent. Do we all understand the second derivative? Is that a yes? Yes? Okay, perfect. Now I need to study the sign. I know it's never 0. So there are no inflection points. This function never changes concavity from moving upward to downward or vice versa. And here's what I do. As I mentioned many times, and I'll say it again, the methods that I show you here, I want you to adopt them if you think that they are worth it. If you know a different method, forget about mine. If you prefer a different method. But what I'm saying here is I need to study the sign of this. And in my mind, this is what I see. This is what I see. Because I don't want to worry about that portion of it. Why don't I want to worry about 12 over x plus 1 squared? So I'm not going to put anything in it. So the sign would be dictated by negative x minus 1. A negative x minus 1 is this. From positive to negative. So I'm done. Crossing at negative 1. Or you plug in a number. So you can say, I don't need to do all this. I can plug this in the calculator and punch in numbers. Fine. I'm fine. For me, it's much easier to separate the quantity that it doesn't matter when it comes to the sign from the rest, and to just worry about -1/x+1. So now we have all the information we need. It's right here. I don't care about anything else. I'm not looking at any page, at any work, just this. So when we graph functions with asymptotes, we have to graph the asymptotes first. So this function has two asymptotes, one which is horizontal and one which is vertical, and the other one that is vertical. A vertical and a horizontal. Okay, now I see 2 points basically. I see 0, -4, and I see 2, 0. The function goes from 2 up to infinity, opening upward. No problem. It should be a little bit closer. I want to graph it closer. It goes asymptotically closer and closer to the vertical asymptote. Okay, on the other side, from -infinity, crossing the y-axis at 0, -4, the x-axis at 2, 0, and approaching 2. No problem. And this is the graph of f of x to x minus 4 over x plus 1. Any questions? Yes, if you want to graph it with the graphing calculator, do not forget the calculator is not as smart as you are. So when you put the function in, make sure you put parentheses, 2x minus 4, in parentheses, divided by x plus 1, close, and you have to put 2 as the second function. The calculator will not graph the horizontal asymptote. You have to put it in. Okay, so then let's say I'm using the standard viewing window, and here it comes from 2 to infinity, from -infinity. Again, I don't know how to make this software present a vertical asymptote. Sorry about that. If you do research it for me, I'll be glad to learn from you. Okay, any questions? Any questions? Any questions?
How did we,
Yes?
how did we determine that y equals 2 is the horizontal for over here? So
By finding the limits.
by 5
We
limits.
found the limits at infinities.
And then, oh, and they're above 2. Gotcha.
Yes. Yeah, for rational function, there's going to be only one horizontal asymptote.
Okay.
Yeah. If it's a combo, it could have a horizontal asymptote at 2 and one at -2. It's possible.
Okay.
But this is not a combo of functions. It's just a rational function.
Okay.
Okay, any questions? Yes, please, huh?
Like for the test,
Yes,
will the table and the graph
will be good enough.
okay.
Yes.
Okay.
Yes. No matter what you do, I recommend summarize the information somehow. So you make it easier on yourself to graph. If you don't like this chart, invent your own. I'm fine. But summarize the information somehow. And I think I showed it last time, maybe not, but these are the steps that we follow. I didn't mention the steps because once you fill up the chart, you're done. So these are the steps. Guidelines for sketching a curve. Domain, intercept, symmetry, asymptotes, intervals of increase, decrease, local max, min, concavity, and sketch the curve. But then, if you just list them like this, I think it's too difficult to put them together without having a table or a summary. So from all this, they come up with that. But they don't summarize the information in any way. It's just a list of A through H. If you say, I don't care for your table. I follow this and I'm fine and I can graph. I'm fine too. If that is better for you, it's better for me. Okay, so we still have work. I'd like us to choose a problem from I don't think we worked on a problem like this yet, have we?
No.
In which we're asked to come up with a graph of a function that fulfills the given conditions.
Yeah, that's one.
Okay, so you want to do that? Please, let's choose any problem you'd like.
You do number 27.
27 it is. Let's look at 27. On page 298. After that, I would like to look at a function with a slant asymptote. Then I would like to look at a function with a hole in the graph. And then other functions that you may want to choose. So we are told that f prime of x is greater than 0 if the absolute value of x is less than 2. We are told that f prime of x is less than 0 if the absolute value of x is greater than 2. We are told that f prime of negative 2 is 0. We are told that the limit of the absolute value of f prime of x when x approaches 2 is infinity. And the second derivative is greater than 0 if x is not 2. Very interesting. I have no idea what this will lead to, but I know for sure that I have to organize my information here. Let's put in the table everything that we have step by step. Ready? Okay. First of all, let's identify what this means. That's our first step. We have to solve the absolute value of x less than 2. What does that mean? What does it mean? The absolute value of x less than 2.
So it would be x
Greater than,
negative 2.
but less than
2.
Awesome. So this is negative 2 less than x less than 2. And the first derivative is positive. So between x being negative 2 and x being 2, between negative 2 and 2, the first derivative is positive, and this is check. Done. Okay, so now let's see what this means. It means that it's not the in-between, but it's this, the outside, greater than 2, greater than 2, less than 2. So to the right, so this changes into two different separate things. Or this. It's everything that is not included in the first inequality. The first inequality said in between. The second inequality says the outside, further away, outside. So it's negative. So this is check, done. F prime of negative 2 is 0. Check. Let's look at the last one and then we'll come back to the limit. The last one says the second derivative is always positive for anything but 2. Okay? Check. Okay, so now let's discuss this one. We don't know whether the first derivative, was it the first derivative or the function? Or did I copy it correctly? Just to make sure. Yes, so it's the absolute value of the first derivative. Okay. So what does this mean? The limit of the absolute value of the derivative is infinity. What does that mean? So when x approaches 2, right, it means that the function is not differentiable, right? If the limit from the derivative from left and right is infinity, what does that mean? Left or right of 2. What happens at 2? No, vertical asymptote. Vertical asymptote. So this is what it means, right? So if the limit from the derivative is infinity, so at x equals 2, so this is where something happens here, right? So first of all, this will be this, undefined, and on this side, infinity, and on this side, infinity. But it's the absolute value. So because it's negative here, it will still be negative. I can't change that sign. The sign is given to us of the first derivative. But it's trying to trick us and say, okay, the limit from the absolute value is positive infinity, but it's the absolute value that makes this side positive as well. But I can't change that. The fact that they are giving us the limit of the absolute value, that does not change the function. Is that clear?
So the derivative function is the absolute value of x.
So, what do you mean? No, so here we're, if we do not have the absolute value, then the limit as x approaches 2 from either side would be d and e. From either side, it would be d and e. Because the limit from one side would be positive infinity, from the other side would be negative infinity. But they're giving us, specifically to confuse us, they're giving us the absolute value of that. But the absolute value would be positive. Because the limit from the derivative, as we see it, if we determine an absolute value, it will always be positive. Every time I put an absolute value on something and the limit in front, the answer will be always positive. Okay. So let's see what we come up with. So obviously at -2, this is a local min. Obviously at this point is a local max. However, the derivative does not exist. And if this one does not exist, this one cannot exist as well. If the first derivative does not exist at 2, the second derivative cannot exist at 2. And obviously that must be a vertical tangent. So let's graph it. So at -2 and at +2. So at -2, it's decreasing because it's a local minimum, and then it's increasing. The function exists, the derivative does not. So I want it to decrease to -2. Don't write anything, I'm trying for a second to make sure. It has to open up at all times. This is a local max, this is -2 and 2. And opening upward, yes. So I want to make it clear that this is a local min. And it goes up. So this is the local min, this is the local max, and you see the tangent here is positive, the tangent here is negative, but it's a vertical tangent. So This is the graph. Of an example of f of x. So decreasing to this point, increasing, decreasing, opening up at all times. The derivative is not defined at 2. Of course, the second derivative will not be defined at 2. And this is our example. Yes, Eddie?
You said neither one of them would be defined at 2. That's where you figured out where that vertical tangent was.
Yes, that is the vertical tangent because the limit from the left of the derivative is positive, the limit from the right is negative, but if I want to determine the limit of the absolute value, of course, they both would be positive. Good. Other questions? Do you think that this is good enough? And can we move on? Or we need more? One more. Very good. Let's choose one more. Okay, ready? Which one? Please, which one? 1, 2, 3. 25. Have you made up your mind? I can change it. Yes?
Yeah, that's good.
Which one? Okay.
Just trying to figure out which one we're gonna, which step what one we're doing.
Okay, 25. A lot of writing. F prime of 0 equals F prime of 2 equals F prime of 4 equals 0. F prime of x positive for x less than 0 or x between 2 and 4. F prime of x less than 0 for x between 0 and 2 or x greater than 4. I chose that one because it was in red and I said, okay, maybe there is something interesting there. 1 less than x less than 3, and the second derivative is less than 0 for x less than 1 or x greater than 3. Okay, so the first condition, I see 0 and 2 and 4. The derivative is 0 at all these points, which makes those critical numbers. Check. Then the second condition says the first derivative is positive for less than 0 and for or between 2 and 4. Check. It's negative between 0 and 2 or greater than 4. Check. Then they're talking about the second derivative, which is positive between 1 and 3. Uh-oh. So the second derivative is positive between 1 and 3. Check. And the second derivative is negative to the left of 1 and to the right of 3. So something happens here because it changes sign. The second derivative changes sign at 1 and at 3. And this is it. This must be an IP. This must be an IP. This must be a local max. This must be a local min. And this must be a local max. So the function increasing is decreases, increasing, decreasing, and this is opening upward, downward, upward, downward. Once you fill up the chart, then from here on, it should be straightforward. Any questions about this? Is this okay?
What is IP again?
Inflection point. IP. Inflection point, local max, local min. Yes. So let's graph. 0, 1, 2, 3, and 4. Something happens at all those points. So it's increasing to 0, comma, a number, anywhere here. So it's increasing, opening downward. I have a pencil right under my nose. I want to write it in pencil first so that I don't have to erase. So let's say I have a maximum here at 0 something. Then at 1, it changes concavity, so it continues to decrease, changing concavity at this point. And at 2, it has a local min. So 1, 2, somewhere here, a local min. And then opening upward, it's going to 3, comma here. At 3, comma whatever, it has an inflection point. It changes concavity, opening downward and decreasing. It goes to a maximum, first of all. It goes to a maximum, and then it changed concavity at 3. Yes, it did, and then it starts decreasing. So this is the function. Local max, concavity change, inflection point, local min, concavity change, inflection point, local max, coming down. So that's an example. Of course, you have many other ways. This is not the only answer. We feel better about this? Is that a yes or a no? Do we feel a little bit better? Yes? No, you had something?
So when you take the second derivative and see that there's a point of inflection, you know that on the graph it's a 0, or it's going to cross the x-axis.
Oh, but it has to.
Okay.
Yeah, if it's an inflection point, the function must exist there. So it cannot change concavity if it's, if it's undefined. Yeah, it could, I guess, it could, but I thought that was my choice to make it exist there and have an inflection point. Because if inflection point has to be a point. I cannot say, I made it have an inflection point, to tell you the truth, right? It can change concavity without an inflection point. But if I choose to have an inflection point, I have to be able to give it to you. Meaning the 1, comma 5 or 1, comma -3. That was my choice. I was not told that it has to have an inflection point. It has to change concavity. I made it. That was my option. I made this point exist. And that's why I said this is 0. But it doesn't have to be 0. And still the function, the problem was not telling us it has an inflection point there. It changes concavity. So, but that was my choice. Very good question, actually. Thank you. Very good. Ready to continue? This time I would like to look at a function with a hole in the graph, because we haven't seen that. And then I'd like to look at functions with slant asymptotes. I would talk about that. These are rational functions. So here's a function for you. rational function. We have to start by identifying its domain. The whole thing is the same thing here. We're asked to graph completely, do everything, find everything, concavity, etc., etc., etc. So we start with the domain. Can anyone give us a domain of this function? And you can say no, just factor the denominator, and then I will. You cannot touch the function before you find the domain. You cannot simplify the function. You cannot do anything to it other than simply factoring it. Now we have to find the domain, and then we can simplify. Eddie, please.
Now,
Go
you're
ahead.
allowed, for this one, you're allowed to take out the X minus one, right?
Not before I say the domain.
Not before.
Not before. Yeah. Before I find the domain, I cannot do that. So what is the domain of this function then?
1, 2.
Yes. So 0, 1, and 2. This function does not exist at 1, does not exist at 2. And now, yes, I can do this. And what changes here is the fact that the factor that went away, which factor went away? X minus 1 went away. That factor does not produce a vertical asymptote because it went away. It produced a hole. X minus 2 stays in the final simplified form because it stays, the limits left and right will be infinity. But here the limits left and right will not be infinity, will be the same number. This becomes a removable discontinuity at this point. Okay, so let's plug in 0 and please tell me what you get when you plug in 0. Perfect. There is no x-intercept because x cannot be 1. So this is 1/2. So now I need these limits. Once we are done with that, we can move on to the first derivative. So we have to find the limit as x approaches negative infinity. Can anyone give us that limit? 1. Can anyone give us the limit as x approaches infinity? 1. Do I have to write that down, or is it clear? I don't think it's clear. Let's do that together. So this is limit of x minus 1 over x minus 2 when x approaches infinity. Eddie, you had a question?
No.
So it's infinity over infinity. When we differentiate using L'Hopital's rule, we get 1 over 1, which is 1. Is that clear? And the same thing with x approaches negative infinity, bless you, if there is no change, because there is no change. So this is 1, and this is 1. Y equals 1 is a horizontal asymptote. Any questions? Okay, now we have these two limits and these two limits. Yes, Noah?
Did you say there was no x-intercept?
Yes, because that is 0 when x is 1.
Okay, gotcha.
So let's determine limit as x approaches 1 from the left of x minus 1 over x minus 2, which will be the same with the limit as x approaches 1 from the right from x minus 1 over x minus 2. Can anyone give us this number? It's not infinity. It's a removable discontinuity. When we plug in 1, what do we get? The top is, and the bottom is -1. So the answer is 0. And now the last two limits before we look at the first derivative. So limit as x approaches 2 from the left of x minus 1 over x minus 2, and limit as x approaches 2 from the right from x minus 1 over x minus 2. We know the answer. It has to be an infinity, one or the other. So the numerator will be positive in both cases. No question there. And the denominator will be 0 in both situations. So 2 from the left is 1.9. What is the sign of the first one? So 1.9,
Oh,
negative, very good. And then 2.1, good. I copy them here. On the left, negative infinity. On the right, positive infinity. We're done with the function. Function is completely done. We determine the limits, we determine X and Y intercepts when they exist, and we determine the horizontal asymptote. There's nothing else. So now we go ahead and differentiate. And we, of course, we differentiate the simplified form. So f prime, the top prime is 1, x minus 2 minus x minus 1 times 1, and this is x minus 2 squared. Nice. X minus 2 minus x plus 1 over x minus 2 squared, which is negative 1 over x minus 2 squared. Okay, so is this function ever 0? No. And it's undefined when at x equals 2, where the function is undefined. So there are no critical numbers. This function will never have max min, because there are no critical numbers. What is the sign of the first derivative? No matter what, always negative. So what does that mean? What does that say about the function? Always decreasing. Let's see. Let's see if we have an error anywhere, or I should say I have an error. From 1 to 1/2 to 0. Is it decreasing? And from 0 to negative infinity, is it decreasing? And from infinity to 1, is it decreasing? So the first two rows, I disregard the domain. The first two rows for f prime and f, they match perfectly. And now we have to determine the second derivative. So here's the second derivative. Of course, I'm going to change this into negative x minus 2 to negative 2. Why? Because it's easier to differentiate. So then the second derivative will be 2 x minus 2 to negative 3 times the inner function prime. So it's 2 over x minus 2 to the third. For the purpose of the sign, it's never 0. There are no inflection points. For the purpose of the sign, you should see this, not this. Because now you know the sign of the first derivative. It must be this. It's dictated by x minus 2. And this is the sequence of signs for x minus 2. And we're done. You don't have to plug in. You don't have to do anything. So before 2 is negative and after 2 is positive. Before 2 is negative, after 2 is positive. And we're done. Of course, it's not symmetric. That's the only thing that I need to, does not fit in the table. So let's graph the function. All I need is the table. All the information is in there. When we graph functions with asymptotes, what do we have to graph first? Yes, the asymptotes. And we have two asymptotes here. We have x equals 2. And we have y equals 1. And now let's look. I have to plot 0, 1/2, and 1, 0. So from 1, decreasing to and cross 0, 1/2, the y-axis, it goes to the hole, and on the left-hand side of the vertical asymptote goes to negative infinity. So that's the first piece. I exaggerated with that hole, sorry. and on the other side from positive infinity to 1. So this is f of x minus 1 squared over x squared minus 3x plus 2. Be careful because the graphing calculator will not show you that whole.